Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Aashna Zainab and Kunari Harris with us today. Hello, Aashna. Hello, Kunari.
Hello.
We'll start with you. Aashna, where are you located at?
I'm in Kolkata, in India, in the
Cool.
eastern India. Yes,
In the eastern part. Okay. And
eastern
how
part of India.
about you, Kunari? Same place?
Well, I'm in Aligarh, is close to Delhi.
Okay.
Delhi, yeah.
Okay, very cool. Let's see, and it is August 21 of 2023 as we record this. And how is the summer going in your respective parts of India? Hot,
It
rainy?
is very humid here in Kolkata.
Okay.
Where-
Let's see. So I'm in Phoenix, and currently we are getting a hurricane, a tropical storm, a typhoon that's coming up Mexico, up the Baja.
Mhm.
And so we have lots of gray skies today. So it's not
Mhm.
quite as hot in Phoenix as normally, but we are a little wetter today. So it's all very cool. Good. And Ashna, what do you like to do for research?
I'm working on the spectroscopic analysis of gold ions,
Mhm.
and mm, I'm currently working on other ions too, like doubly ionized and quadruply ionized ions.
Cool. And Kunari, what do you like to do for research?
Well, I did my PhD in spectral analysis of tin atoms,
Cool.
and then I did my postdoc at NIST. I worked with Alexander Kremida on critical evaluation of atomic data, and later I joined Aligarh Muslim University.
Uh-huh.
Now I am working as an assistant professor on
Cool.
contract here. Yeah.
Very cool. Good. And that is going to bring us to this very awesome APJ supplement article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. Critically evaluated atomic data for the gold 4 spectrum. And Ashna and Kunari take us away.
Okay, before I start, I would like to thank you for giving us the opportunity to present our work. And I would also like to thank our collaborators, that is Sebastian and Pascal from Belgium, who provided us with HFR, CPOL, and MCDHF calculations for our gold ion. And also A. Tohi, he's from our department only, under whom I completed my PhD.
Cool.
So in this work, we did the spectral investigation of triply ionized gold atom in the vacuum ultraviolet region. So now the
Okay.
first question that arises, that why we chose high Z elements such as gold to study. So this the highs. I would like to mention the fact that high Z elements have lately gained very much interest. This is due to the fact that firstly, this the it these elements were found to be present in the spectra of many chemically peculiar stars such as AGM and Kailupi and Kailupi stars, and there. mm, okay, I cannot see this. Wait, this is a problem. Okay.
You good?
Okay, the paper. Wait, I'm not able to see the paper.
Okay. Let me go ahead and stop the share and I'll start it again. Let's see what happens. Screen share. How about now?
Okay, okay, now it is visible.
Okay.
Okay,
Bandwidth.
so these high Z elements are are found in the spectrum of this chemically peculiar stars, and in turn these spectrum can be used to found the abundances of these elements in those stars. So these generally triply ionized gold is not directly found in any is not directly observed in any star, but it's the case that these high charge state ions, that is triply ionized, doubly ionized, all these spectra are very dense in nature. Therefore they overlap with each other.
Ah,
So to have the accurate line identification and accurate the results, so we have to, so it is useful to do the spectroscopy of the adjacent ions also. So therefore we did the spectral analysis of this ion. And secondly, this ion, these high Z ions also gained much astrophysical interest when the gravitational waves were detected. This is okay. This is because the observations and the this the observations of these gravitational waves supported the fact that these high Z elements are formed in such neutron star mergers in these kind of celestial events by a chain of reaction. So to explain and model the observed spectra of for the observed kilonova spectra, so large sets of calibrated atomic data are needed. Atomic data are needed for these ions, the high Z ions, and also data on the ionization species. So in this regard, atomic data for these ions are required, and this for this electric dipole and the electric dipole as well as forbidden transitions are both important for the correct interpretation of the kilonova spectra.
cool. Good.
So basically, gold ions are found in many astrophysical objects, but and but only the data on the electric dipole transitions are only available in literature, not
Okay.
and any forbidden transitions of this gold 4 ion has not been yet reported now, till now. So, and these data or these this calibrated data also help in improving the accuracy of theoretical calculations of complex ions.
Great.
So so therefore these critically evaluated and calibrated data are needed are needed. And this gold ion, gold 4 triply ionized gold ion, that is gold 4, is a very heavy ion, and it's belong to osmium 1 isoelectronic sequence.
Okay.
And its ground configuration is 4f14 5p6 5d8, which alone consist of 9 energy levels. And its regular excited configurations are of the type 5D 5d7 NL, and sometimes two or three electrons jump and form much complex structures.
Ah,
And all these complex configurations have been included in our calculations for better accuracy.
cool.
So therefore, in our work, we have critically evaluated all the previous reported data on AU4 using Hartree-Fock method, and also provided theoretical support for our observations. Using core polarization effects, we have also calculated accurate transition rates for the gold 4 ion.
Okay, cool.
Okay. So now moving on to the experimental details.
Okay.
So the recording of the gold spectra was done at NIST, USA, and it has been recorded on this 10.7 meter normal incidence vacuum spectrograph in
Okay.
the wavelength in vacuum ultraviolet region. And the dispersive element used in this was a grating whose dispersion factor was 0.78 angstrom per millimeter.
Okay.
And additionally, we have other plates also from the Antigonish laboratory, which were recorded on 3-meter normal incidence vacuum spectrograph. But
Okay.
those plates were only used for the ionization separation purpose.
Okay.
Okay, and the main whole, the measurement and the calibration, everything was done using the NIST plates.
Okay.
So on these, in total, in vacuum ultraviolet region, in total we had 7 plates, and in each plate, several tracks were recorded at different experimental conditions.
Okay.
And it was observed that lines of different ionizations exhibit different characteristics. So, the track which had the prominent bold 4 lines was selected, and they were measured using a Zeiss Abbey comparator at a laboratory, and their positions as well as their visual intensities were recorded.
Okay.
And then those spectrograms were then calibrated using some internal standards, highly accurate internal standards,
Mhm.
and these values were taken from the NIST database. And these wavelengths which we calibrated had some internal uncertainties, which we also incorporated and calculated. And
Cool.
these uncertainties are combined effect of two things. Firstly is the statistical deviation of the line positions which we measured on the comparator, and
Mhm.
second is the systematic uncertainty due to the this reference lines.
Okay.
So by incorporating both these uncertainties, and we found that the final uncertainty for the sharp and unblended lines
Okay.
were 0.005 angstrom, which was
Nice.
fairly good.
Nice. Very nice.
Okay,
Beautiful.
so now moving to the analysis of the spectrum. So the first insight of that, the first work which was done on this ion was done in 1991 by Joshi's group,
Mhm.
and they just oh my god, they just did the resonance transitions, that is from ground to
Okay.
5D 6P, this resonance transitions array in a very smaller wavelength region. And they, on the basis of classification of 196 lines, they
Okay.
were able to establish 8 out of 9 levels of the ground configuration 5D8,
Okay.
and 64 out of 110 levels of 5D7 6P configuration.
Good.
And this work was then extended by Vyard in 1994, and he extended his work by introducing a new transition array, that is the transitions from connecting from 5D7 6S to 5D7 6P.
Okay.
And he also he established 33 levels, almost 80% levels of the 6S configuration and also 6P configuration. So and his estimated accuracy for the measurement was 0.007 angstrom.
Okay.
So what we did, that what we when we started our investigation, so we started with verification of the previously reported data of cold floor.
Yeah.
So
Yes.
while we were investigating that, we found we were able to revise one level of the 6P configuration 6P configuration, which was reported by Joshi, and
Uh-huh.
we were also able to find 2 new levels of 6P. And most importantly, the ground, the singlet S0 level of the ground configuration, which was unknown still, we were
Okay.
able to establish that level,
Nice.
which and we were able to establish at like 5.52778 centimeter inverse, and
Okay.
which was really close to the predicted value of this level. So
Cool.
this so after this, all the levels of the ground configuration were calculated, and the parameters and new parameters were now generated for the ground configuration.
Yes.
And so in total, in our work, we were on the basis of classification of 1031 transitions, we were able to establish 139 energy levels.
Nice.
So,
Very cool.
and so once sorry once then all these energy levels are established, and we have noted the transitions. Now the next step is to optimize those energy levels.
Okay.
It means optimize this in optimization is basically is finds the best fitted energy level value for those levels.
Yes.
And it also helps in checking the consistency of the line classification what we did, because in this the observed wavelengths are then compared to the RITS wavelengths. So
Okay.
in this we can check the consistency of those lines.
I'm with you.
So
Yep.
basically it's an iterative process.
Yes.
And in the end the result, and when the convergence is obtained, we obtain a final list of RITS wavelength along with its uncertainty.
Okay.
And and these and obviously RITS wavelengths are more accurate than the observed wavelengths. So these wavelengths are then used as the reference to check the previous measurements.
Good. Okay.
So and it was observed that the agreement between the corrected and the RITS wavelength was 0.005 angstrom, which was
That's
satisfactorily good result.
very good.
And
Very good.
now moving to reduction of line intensities. Now, as I mentioned earlier, that when we were recording the spectrum, when we were measuring the spectrum, we visually estimated the intensities of those lines. But obviously, that visual estimation has bound to have errors. First thing,
Yes.
and secondly, many these lines and observations are present from multiple sources, previous works. So we cannot compare these different sets of data. The
Okay.
intensities cannot be compared. So what we do that by in this by LTE, we use this approximation of local thermodynamic equilibrium,
Uh-huh.
in which what we do in this we reduce all the intensities to a common scale for the comparison purpose.
Yes.
So, so in this method, we find the effective excitation temperature of the source, source of the different experiments of the previous work and art, and then we take one temperature as the basis, and
Okay.
then at that temperature we mm, uh, we reduce to the common scale.
Right.
So in this case, we have two sets of observation. Firstly, from our case, and secondly from the previous work's case.
Yes.
So from the previous work, what we from the previous work, the excitation temperature was found to be 5.3 electron volt,
Yeah.
and from our case that was found 5.5 electron volt. So we chose our temperature as the basis
Okay.
for reducing the intensity, and then all the intensities were corrected and shown in and tabulated in table 1. And also, if common lines are available from different sources, then we average all those
Okay.
intensities uh, if they agreed within one standard deviation. And if any line, or if any reason the line if there is a means it is not agreeing, then we have excluded from those that averaging, and that line is mentioned as marked as X in the tables.
Okay.
So here you can see this table 1 of the classified lines of board 4. So the first column represents the model intensities, which we reduced the intensities on a common scale at 5.5 electron volt.
Right.
And you can see the second is the character, which defines the character of the line, whether it is hazy or diffuse or anything. And
Mm-hmm.
then the wavelength, and the observed wavelength and RITS wavelength along with the uncertainties are given, and also their classification.
Cool.
And for all the transitions we have mentioned the transition rates calculated from two different methods, that is HFR CPOL and HFR,
Mm-hmm.
and the accuracy have also been mentioned in the column, and and the accuracy have been coded like A, B, C, D, and it has been explained in the um, other table.
Yes.
And in table 2, you can move to table 2.
Optimizing.
And this is the table of optimized energy level values of AU4. In here, you can see the energy level values of all the levels, and along with their uncertainty and LS percentage composition.
Okay. Mm-hmm.
So, okay, now my co-author will take take you from theoretical interpretation.
Okay. Do you want to cover?
Hello. Yeah.
Page
Can you hear?
6.
Yeah, yeah.
Mm-hmm. Can I go down?
Sure.
Yeah, here.
Mm-hmm.
So we have the observation. So in order to interpret these observation, we need to have theoretical models. So we did three models: HFR model and HFR plus CPOL model, and we have the MCDHF calculations.
Okay.
So
Mm-hmm.
The advantage of having HFR and CPOL model is that we can do the least square adjusting of the theoretical, observation with respect to the experimental energy levels.
Okay, I'm with you.
So
Mm-hmm.
we did that. So and in HFR model, we have included only the valence electron correlation, but in our extended this HFR plus CPOL model, we included additionally the core valence interactions by
Okay.
considering the CPOL contribution for AU6 ionic core,
Okay.
and for which the important parameters were the dipole polarizability as well as the cutoff radius of this particular
Okay.
AU6 ionic core.
Yes. Yes.
And both of these models compute the radiative transition parameters for several observed as well as for possibly observed lines of allowed and forbidden types.
Okay.
And then the MCDHF calculations we performed, particularly to compute the radiative transition rates for the forbidden transitions, which are of astrophysical interest.
Yes. Good stuff.
And then once we have the model from which we have all these radiative transition rate, then we go to the evaluation of these transition data. Can I go down?
Evaluation. Okay, I'm with you. Mm-hmm.
All right, yeah. So the evaluation of transition rates, so we have two type of transitions. One are allowed E1 type transitions,
Right.
which we can see on this energy level diagram, figure 3,
Yes.
where these transitions are E1 type, and these are forbidden types. This So we have huge amount of data, about 2,000 lines for the allowed transitions and about 800 lines for the forbidden spectrum.
Cool. Very nice.
Yeah.
Mm-hmm.
So the for the allowed transitions, what we did is that so we have HFR plus and HFR plus CPOL calculations.
Yes.
So we found that the HFR lifetime data are systematically lower compared to the HFR CPOL model data.
Okay.
So we need to have an adjustment. So we did an adjustment of the HFR data,
Okay.
lifetime data, to the HFR CPO level.
Okay.
And this is an indirect adjustment which come from the study of the isoelectronic sequence, for example osmium 1 as well as this iridium 2 spectrum, which are the lower members of the isoelectronic of this spectrum.
Right.
And where we have the experimental lifetime data available. So we did a comparison of the experimental data with those HFR plus CPOL results. So
Okay.
where we found that their agreement is between 20 to 30% for these ions.
Very good. Okay.
So once we have the adjusted lifetime data from these adjusted HFR lifetime data, we have our transition probabilities, which are sort of adjusted. And those adjusted transition probabilities are again used for the computation of the line strength. So we computed the line strength for the electrically dipole allowed transition using this formula
Okay.
here here in the bottom. Yeah,
This one right here. There we go.
yeah, yeah.
Yep.
So then once we have the line strength, then we made a comparison of these line strength from these two model, HFR and HFR plus C-pole model.
I'm with
Can you
you.
go to the, yeah, the figure now? Yeah,
Figure 4.
yeah, figure 4. So here is the figure where you can see, can I pop it up? Yep. Yeah, here is the figure. We have the logarithmic comparison of the HFR and CPOL along the HFR CPOL. Here we have divided these data into three based on their cancellation factor.
Okay.
So
CF.
these are the transitions which are less affected with the cancellation effect. These are moderately affected transitions. These are highly the affected transition to the cancellation effect. So we evaluated them separately as
Okay.
a function of this line strength of HFR plus CPO.
Yes.
And the results are given in table 1, which Aashna already discussed, and the accuracies are summarized in table 4.
Let's go to table 4 or
It's,
to next door. Here we
yeah,
go.
next, yeah. So these are the uncertainties from these two set of data based on their CF type as well as their absolute line strength.
Yes. Okay. I'm with you.
Yeah, and then we had to do add an additional term for this statistical component of this uncertainties.
Okay.
There is another systematic component about 30%, which come from the comparison of the lifetime data from the isoelectronic members.
Okay.
So that additional component is 30%,
Okay.
and together with the these are the uncertainties, the next column of the table 4.
Oh, sorry. Gotcha.
Yeah, here is the simple and here is the
Yep.
final uncertainties
Okay.
for each of these transitions.
We'll click.
This table is also the table which can be used for finding the transition, for interpreting the transition uncertainties of the forbidden transition as well. So this is a common table for the allowed as well as the forbidden transitions. Yeah.
Okay. That's the M1 plus C2s. Okay.
So can you go down?
Sure. Forbiddens.
Yeah.
Table
Then
5.
we have the forbidden M1 and E2 type of transitions,
Yes.
which are essentially of inter configuration and inter configuration type as well as intra configuration types. So these are the two transition. They are within the levels of 5D8 as
Yeah.
well as they are of 5D8 to 6s.
Okay.
Uh,
Okay. Mm-hmm. All right.
So, as I said, we have three set of models for this forbidden spectrum. We have HFR, we have HFR plus CPOL, as well
Yeah.
as MCDHF calculations.
Yes.
So, we have performed a better systematic comparison for this case of spectrum compared to the allowed transitions. So for HFR model itself, we have made a Monte Carlo simulation for about 20 trials to estimate the internal uncertainty of A values or S values, which
Okay.
and in general, we have a good agreement between the HFR and HFR plus CPOL
Okay.
within 0.3 dex, and then we have for final uncertainty estimate, we made a final comparison of the HFR plus CPOL with our MCDF results.
Okay. Good. Mm-hmm.
And also we did a lifetime comparison, which we summarized in the table 5.
Should we go to table 5? Let's take a look at
Yeah.
table 5. Table 5.
Yeah.
Very nice. Oh, very nice.
Yeah. Here we have a table where we have the levels. These are all the levels of 4D8, 5D8, as well as 5D7 6s.
Cool.
And these are the theoretical, the difference between the observed and the theoretical MCDHF levels.
Okay.
So you can see a quite good agreement here of the MCDHF as well as with the observation. And then we have the MCDHF lifetime data in two form, in velocity form as well as in length form.
Got it.
So these are sort of internal consistency of the calculation.
Mm-hmm.
And then we have the result here. We have shown the HFR plus CPOL results only.
Mm-hmm.
And in table 6, we have summarized the computer rates wavelength and the radiated transition parameters for the forbidden AE4 lines along with their uncertainty. So this is the long table
Yes.
of 800 lines. Yeah.
Right. So just to make that clear, this is not the complete table, people. There's a machine readable table that has the whole thing.
Yeah.
This is just an example of what's in there. Uh-huh.
Yeah, exactly.
Mm-hmm.
So then can you go to the next session?
Sure. Sure.
Yeah.
Conclusions?
I think before that we have section 8.
Ah, gotcha. We missed it.
Yeah.
Yeah. Right.
Yeah, right.
The
Yeah,
opacity.
exactly.
Right. Opacity. Mm-hmm.
Yeah. So, so as Aashna interpreted there in the introduction, the transition data, there are we have explained these transition data. Uh, excuse me, I can't see it.
Can't see the article. Okay, let's try that again. So I'm going to stop it and I'm going to start it again.
Mm-hmm.
Let's try that again. Got some bandwidth issues.
So, is it? Am I audible now?
Yeah, we're up.
Yes.
Yeah. All right. So, so the table one, the transition data in table one, as well as the table six, these are limited set of data. Indeed, we need a large set of data for kilonova, interpreting the kilonova's black body spectrum.
Yes. Okay.
So for that, we found that there are two literature, one from Tanaka, another from Tagadumi.
Right.
These two results are already there for A4 spectrum. These are large-scale atomic data. And then these what we did is we need to have a comparison with our HFR result. So so in order to do that, we did a similar comparison with respect to their S values. We found that the disagreement between the Tanaka result or Tagadomi, they are with respect to our calculations, they are very large. They are about 100% for transition with their line strength greater than or equal to 10.
Yikes.
And the disagreement is increasing with the decreasing value of the line strength. It's about 500%. So, yeah.
Okay, that's a big difference.
Yeah. So we decided to have a better data. So we decided to produce a better large scale data for this for a few selector levels. Can you go down?
Sure. Yep.
Yeah.
Yeah. Okay.
So we have obtained these levels 4D8, 5D8, and can you? Yeah, just highlight here. Yeah, for these levels, since for most of these configuration, we have better interaction configuration interaction accounted for. So thereby we have computed the radiative line parameters for about 95,000 even type of transition between about 1,000 levels.
Cool. Very cool.
Yeah, all these data are supplemented in this database Zenedo.
Very nice.
Yeah.
Cool.
So in conclusion, we have critically evaluated the A4 spectrum in the wavelength region of 500 to 2000 angstrom. And we have provided the theoretical interpretation with the help of Kovan Institute of Codes. And we have established about 139 energy levels with the help of 980 transitions.
Cool.
Can you go up?
Yeah.
Yep. And we have provided the rich wavelength with their uncertainties. These rich wavelengths are computed from the optimized energy levels. And we have provided the forbidden spectrum for first time, the extended, forbidden spectrum of A4 for first time. We have provided the transition rate for M1 as well as even type of transitions. And from the three different calculations. And besides that, we have also provided the large-scale atomic data with the specific application to compute the opacity of AU4 in the kilonova ejecta, and which we have supplemented in Zenedo database. Yeah.
Very cool. Very nice. Very nice. Beautiful work. Beautiful work. Aashna, Kunari, thank you so much for walking us through your very lovely article. Very
Thank
nice
you.
work.
Thank you.
Yeah, and yeah, so you kind of mentioned it a little bit, So let me go ahead and touch. Where do we go from here, given the published article? Is there more data to take on AU4? Does one go after other ionization levels? Does one go after other elements? Is there additional theoretical work that could be done? Experimental programs going? So just sort of where do we go with this over the next, let's say, 2 to 5 years? Aashna, why don't you start?
So we are working on the other ionization stages of gold,
Okay.
like doubly ionized and quadruply ionized.
Okay.
So hopefully, two papers are on the way in next 2 to 5 years.
Very good.
Hopefully.
Cross fingers. Very cool. And Kunari, how about you? Where do you think we go with this over the next couple of years?
Well, yeah, we have, well, I can explain there are some shortcoming of the present data. In fact, there are, for example, can you pop the article? I can explain there.
Sure. One sec.
Yeah. Can you go to the page down?
Page down.
Yeah, just
Experimental details, analysis of the spectrum, reduction in line intensity.
Section 6, yeah, where
Section
we have
6.
theory. Yeah.
Yes. Okay.
Can you go to the figure?
Which one?
There is energy level figure on energy levels. Yeah.
Figure 3. That's our energy level diagram.
So we so far we have studied these 3 configurations. There are plenty of other configurations which are there. So these are worth to study in future. As well, we have the present theoretical MCDHF results are not good for this E1 type of transition. So this is something to do in future. So we need to have a better calculation for these E1 transitions using this MCDHF calculations.
Okay.
Yeah, that's all. Yeah.
Okay. Very cool.
All right.
Very nice. So we have some experimental work going, we have some theoretical work going. It'll be really great. It'll be really exciting to see this develop over the next couple of years, and we'll get several ionizations of gold. So very nice. Cool. Aashna and Kunari, thank you once again for agreeing to talk about your very lovely article. Thanks.
All right.
Thank you.
Thank you.
And that will do, everyone. And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.
All right. Thank you. Bye-bye.
Bye-bye.